All right, guys, welcome back. This is going to be 6.4. And what we've been doing is learning about equations of lines. We've learned about slope-intercept form, and we learned about standard form so far. And so you'll get later why you're a transformer, because you're going to transform equations. But we've learned that if two different types of equations of lines. If we have a slope and a y-intercept, we can use the slope-intercept form. Seems pretty self-explanatory. Remember, that was y equals mx plus b. If you don't remember that, that's 6.2. Pop back over to that video or look back at your notes from class and check those out. We also learned in 6.3 that standard form is really good for the x and the y-intercepts. This is when we set everything to 0 at different points and solve the equation, found the intercepts and graphed it. Okay, if you don't remember that, look at the 6.3 video or your 6.3 notes. But what can we do when we want to graph something given only a slope and a coordinate point? If I have a graph that only has a single point on it and a line running through it, and I know the slope of that line, how can I write the equation of the line? It's what we're going to learn about in 6.4 today. Okay? Well, to do this, I want you to think about the formula for slope. And this really goes back to 6.1, rate of change. We learned 3 different formulas, rise over run, change in dependent, change in independent, or Mr. Carter's personal favorite, y2 minus y1 over x2 minus x1. Okay, so we got this formula. Well, how can this help us set up an equation for a line? Actually, it can be really useful. You see, one of the things I know you have learned in algebra is that to move something from one side to the other, we can do the opposite. And while it may look complicated with all the letters going on here, fundamentally, the denominator, y2 minus y1, is being divided by x2 minus x1. So if I want to move x2 minus x1 to the other side of this equation, all I would have to do is multiply both sides by x2 minus x1. Might look a little weird because we're doing it all with variables, but we've done this type of algebra before. The whole right side's being divided by x2 minus x1. So if I multiply both sides by x2 minus x1, I can move it to the other side. When I do this, I end up with m times x2 minus x1 equals y2 minus y1. Now I'm going to do a little manipulating and rewriting here. But this formula that we're going to learn about today is the formula we're going to use for when we have the situations where we have a point and a slope. Okay? This right here is known as, and again, I've just slightly rewritten it from what we did above, is point slope form. Point slope form. Okay? Again, point slope form, write it down right here, y minus y1 equals m times x2 minus x1. It's our third formula for the equation of the line, and our last formula we're going to learn. Okay? So what is point slope form? Let me back up a bit. What are the features of the point slope form? Sorry. Well, what you're going to do, and really why I changed some of the labels, is you are going to leave the y and the x as they are, kind of as we do in slope-intercept form and in standard form. Y and x are just y and x. you will plug your point in for y1 and x1. What am I talking about? Well, point-slope form implies you have a point and a slope. You will be plugging your coordinate point, namely the y value, in for y1 and your x value in for x1. Y and x stay as variables just like they do in standard form and slope-intercept form. So those are just variables. And m is going to act as your slope. M is going to act as your slope. Now at this point, now that we kind of know what point-slope form is, we see the different parts. Why are we learning it and what can we do with it? Well, it's really useful because, again, if I don't have 2 points, if I don't know the intercept, okay, if I don't have the y-intercept, and but I do have a point and I have a slope, I can create the equation of a line. You'll quickly find that point-slope form is probably the most useful form. And in turn, we can turn it into slope-intercept form, which is really nice to work with. We also can graph and use rise over run with it. Okay? So you've kind of learned some theory about point-slope form. Well, where are you actually going to use it? Well, let's start with graphing. Okay? If you feel confident you've seen point-slope form before and you want to try graphing with it, go ahead and try it. Pause this video and try and graph the equation y minus 5 equals 12 times x minus 2. But if you aren't feeling super confident with it, what I want you to do is go ahead and follow along with me. So pause that video and give it a shot. Or stick with me. Okay? So hopefully if you've wanted to solve it by yourself, you've paused it, you solved it. If you're with me, let's do it together. Point-slope form, remember, has a few different parts. We've got our variables, y and x. y1 and x1 are our points, and the slope is m. Well, I notice here that 12 is my slope. M equals 12. 12 is my slope. In point-slope form, what makes up my coordinate point, because again, you have a point and a slope, are these 2 values. Now, where point-slope form can be tricky is you see the minus signs, and you go, okay, so minus 5, minus 2, or minus 2, minus 5 is my coordinate point, right? Well, kind of, but it's not negative. You see, if you look at the original formula, the minuses are already built in there. Again, they're built in there because it comes from point-slope form, comes from the formula for slope. So since the minuses are already built in there, the actual coordinate point here is x1, y1. The minuses come in just as part of the equation. So it's weird, but it seems backwards, but when you see minus x1 minus y1, it means x1 and y1 are positive. If these were positive, it would actually mean your coordinate point was minus x1 and minus y1. Now, if that's confusing to you, just take note of it and we'll practice it more as we do it together. Okay? But essentially, the signs in point-slope form are going to flip-flop. So back to my problem here, I've got minus 5 as my y point, which the minus is just part of the equation. So my actual coordinate point would be positive 5 for the y and positive 2 for the x. Now that given the equation, I have pulled out my slope and my point, I'm going to go ahead and plot my point and then graph with my slope. Now, since my slope is so significant, it's 12, which means it's going to be up 12 over 1. I'm going to change the scale of my graph a bit. I'm going to go up by 5s. Okay, and then I will still go over by 1s. So what am I going to do? Well, I'm going to plot a dot at 2, 5, because that's my point. Then I'm going to go follow my slope. So I'm going to go up 12 to about 17. and over 1. Up 12, so 29 and over 1. Okay? And then I draw my line. Again, what do you need to walk away with knowing? What I need you to be able to do is when you see point-slope form, recognize how to take out the slope and how to take out the point from what you're given. Okay? If you have questions about this or you're confused right now, go ahead and shoot me an email about this concept. All right, moving on. By the way, just as your friendly reminder, please make sure you're taking notes throughout all these videos, just like you would in class. Okay, so now we want to write the equation of the line given a slope and a point. Then we want to change it into slope-intercept form. Well, let's tackle the first part. You're given a slope, you're given a point. Hopefully your brain's thinking point-slope form. Not because of it's just the topic of the lesson, but because when you have a point and a slope, hopefully your brain says point-slope form. The name's kind of self-explanatory. So I've got my formula for point-slope form. Well, they give me a slope of -3. Now I just have to fill in my points. Well, my y-coordinate is +7. Remember, the minuses, as you've seen, I've already written them, come along with the equation. So I'm going to plug in 7, and I'm going to plug in -1. But again, notice the minuses come along with the equation. So it looks weird, but the +7 becomes y minus 7. Over with the x, you can see I have x minus -1. Two negatives make a positive. So this gets rewritten as y minus 7 equals -3 times x plus 1. Again, when it comes to the x and y variables, your sign is going to look opposite. So your first step here, given the point and the slope, here's how you write the equation in point-slope form. Okay, now that we have the equation in point-slope form, we want to turn it into slope-intercept form. Now, if you remember in 6.3, we spent time turning slope-intercept form into standard form, okay? So to turn something into a different form, you have to know the features of that form. We knew that standard form had no fractions and all the variables were on the same side. Slope-intercept form, what is unique about it? Y is by itself. And there are no parentheses. Y is by itself, and there are no parentheses. So I have a formula in point-slope form, but I want to turn it into slope-intercept. Well, I need to get rid of the parentheses and get y by itself. Now, unlike what we do with standard form with getting rid of fractions, which might be somewhat complicated, this is pretty easy, and you've been doing this. How am I going to get rid of the parentheses? Distribute that -3 through. And I get y minus 7 equals -3x minus 3. Okay? You've been doing this since chapter 2. Just go ahead and distribute that -3. Now to get y by itself, what can we do? We can add 7 to both sides. And we get y equals -3x plus 4. Again, what's crazy about this is these two equations are the exact same thing, though they look very different. The one in black is just in point-slope form. The one in blue is just in slope-intercept. What you need to know, though, again, one, recognize how we can take a slope and a point and where they go in the point-slope form, not forgetting that your signs flip for the y and the x. And then to turn it into slope-intercept, you want to get y alone, and you want to make sure there are no parentheses. Again, if you're confused about anything I've done here, go ahead and pause the video and rewatch that segment, taking good notes, or if you're still confused, shoot me an email. But for now, we will keep plugging along. Now what we want to do is we want to try to write the equation of a line given 2 points. Again, what you're learning all in Chapter 6 is how to write the equations of lines given certain circumstances. What if you have the intercepts? Standard form. What if you have a slope and an intercept? Slope-intercept form. Point and a slope, point slope form. Now what do we do if we just have two coordinate points? Well, what you can do is you can use the 2 points as we learned in 6.1 with coordinate points to find the slope. Then pick one of the points and use point slope form. Let's do an example. So number one, when you're given 2 points, if you like steps, find the slope. When we're given 2 points, how do we write the equation of a line? Start by finding the slope. This is what we did in 6.1. We label our points x1, y1, x2, y2. And then we go ahead and find the slope. How do we find slope? y2 minus y1 over x2 minus x1. What I'm going to do at this point is plug in my values at the appropriate location. 3 minus -5 divided by 3 minus -1, which gives me 3 plus 5 over 3 plus 1, because 2 negatives become a positive. I get 8 over 4, which is 2. So step 1, find your slope. I have found the slope to be 2. If you're still writing your work, pause the video because I'm going to erase this for the interest of space. Okay, so we found our slope. Our slope was m equals 2. Now that we have a slope, we have 2 points. So what you're going to do is plug in one of the points to point slope form. Does it matter which point you plug in? Nope. You can use either point you want. If I want to write an equation of a line given 2 points, all I do is I find the slope. Then I'm going to fill in the slope and pick my favorite point. If you wanted to do the first point, remember the signs flip. So it would be y plus 5 and x plus 1. If you didn't want to do those, you could have also written your equation of a line as y minus 3, x minus 3. Either way, it gives you an equation of a line. So what do we do when we have 2 points in the slope? How do we find the equation of a line? You want to find the slope and then plug in one of your favorite points. All right, again, you can see this video has a lot of chunks to it. We do a little bit, pause, do a little bit more. I'm going to pause here again. If you are confused about how to find the equation of a line, finding the slope, and plugging in a point, shoot me an email at this point. So where do we go from here? Well, now we want to try and utilize the table to inform us about whether the data creates a line or not. What I hope you're seeing with chapter 6 in general is we just do a bunch of little mini situations where we try and do different things with lines. You know, we have a point and a slope. How do we make a line? We've got 2 points. How do we come up with a line? We've got a table. Is it a line or not? Okay? So we want to use the table to figure out whether the data creates a line or not. If it does, use point slope form to write the equation of a line. What I want you to do is I want you to think back to what I said about slope and tables and something being a line or not. If you remember in 6.2, we played hangman to figure out if something was linear or not. And in 6.1, we actually looked at an example at the very beginning when we were first looking at rate of change of something that wasn't linear. You think of it? Well, pause the video and think about it. Okay, now that you've thought about it, what I hope you remember is that if the slope is consistent between points, it is a line. If slope is inconsistent between points in a table, it is not a line. Okay? Now, you might be going, what the heck, Mr. Carter? We have not learned about this yet. Well, we actually did. Think about the toast example at the very beginning of 6-1. We talked about rate of change at different points, but you remember very clearly what that graph looked like, and it looked like a step stool. It was going up like this, and then it shot up, and then it went like that, and then it increased a little bit, and then it went like that. That is very clearly visually not a line. What's the moral of the story? The rate of change was different between different points. So if the slope is consistent between all points, something will be a line. Flash forward, we're going to use the table to figure out whether the data creates a line or not. And then if it does, use point slope to write the equation for a line. Well, step one, to figure out if it's a line or not, I got to look at this table. If this table has consistent slope between points, then we can make a line. If it doesn't, then we cannot. Okay? So I'm going to find the slope between some different points here. If you're thinking back to our tables in 6-1, how did we find slope? All we do, y2 minus y1 over x2 minus x1, or the change in dependent over the change in independent. Either way, we should be doing 6 minus 4 over 3 minus negative 1. Again, if this doesn't feel familiar, jump back to 6.1 notes, and you'll see we did this similarly with tables. Okay? 6 minus 4 is 2. 3 minus negative 1 is 4, giving me a slope of 1/2. Okay? Let's try the next set of points. Seven minus 6 over 5 minus 3. Again, your y is always going to be your dependent. X will be your independent, which is why the y is on top. 7 minus 6 is 1. 5 minus 3 is 2. Again, we have that k. We're doing pretty good. Consistent slope of 1/2. Let's try the last set of points. 10 minus 7 is 3. And 11 minus 5, 3 over 6, which again is equal to 1/2. And we could even go from 10 to 4 and then 11 to negative 1. You could go from 10 to 6 and 11 to 3. The slope is consistently 1/2. So we know we have a line on our hands. No matter where you go in the table, the slope is 1/2. Now, folks, this is no different than the 2-point example we just did. It might seem a little different, and we had to do a bit different steps to find the slope, but writing the equation of the line is the same. We know from point slope form we have y minus some point plus the slope, and then x minus some point. Pick a point in the table. I don't care which one. Any of them will work. I will do y minus 6 and x minus 3. And boom, there is the equation of the line. If I wanted to graph it, what I would do is I would go to my point, 3, 6, and I would simply go up 1 over 2. I could go down 1 and left 2. And there's my line. What's really cool about this is if I kept plotting points, I would eventually find that all of these points will fall right in line with that line I have created. So moral of the story to this point. We can use, through various different methods, point slope form kind of turns into our jack of all trades. Why? Because you only need a point in the slope. We learned what point slope is. Then we learned how to transition it to slope intercept form. We learned how to graph with point slope. And then we learned how, given 2 points, to use point slope form to write the equation of a line. Then we learned how to come up with an equation of a line out of a table, again, using point slope form. If any of that's confusing or you don't remember that, jump back to different parts in the video and you see we tried all those different things. So where do we go from here? We got one more example to go. Wouldn't be a Mr. Carter lesson without a word problem. So what do we do here? Well, Mr. Carter, in my excessive amounts of free time, not really, travels the United States, and I boil water at different altitudes. Below is a table of the different altitudes I have done this at and the different temperatures. So you can see the table there. We want to find the table whether the data creates a line or not. If it does, use point slope form to write the equation for the line. Okay? I want you to pause this video and I want you to try this on your own. It's just like the problem we just did. I'll scroll up so you have the problem in view. Try this problem. Utilize the table. See if it creates a line, and if it does, write the equation of the line in point slope form for me. Okay. Hopefully you've paused the video, you've taken some time and tried it, and now you want to see if you did it right. Well, the first things first is we got to make sure that we have consistent slope. Okay? Consistent slope. So, what am I going to do? Well, my altitude is going to act like my dependent variable, or my independent variable. And my dependent variable will be my temperature. Depending on the height we're at, determines what temperature the water will boil at. Okay? So we got to find a consistent slope. Remember always, changing dependent over independent. You could also think of this as the y and this is the x. y2 minus y1 over x2 minus x1. So we got to try the different points to see if there's a consistent slope. 203.9 minus 197.6 divided by 4.5 minus 8. Okay? When I do this in my calculator, 203.9 minus 197.6 over 4.5 minus 8, I get negative 1.8. If I do the same thing, 206.6 minus 203.9 and 3 minus 4.5, you will get the same slope of minus 1.8. In fact, if you go from any y value to any other y value, and you do the same thing with the x's, you will get that consistent slope of negative 1.8. And you probably tried a few more points than I did, which you should, just to speed up the process. The slope turns out to be negative 1.8, as you saw in our first example, and it is consistent for the others. So the last step, how do we write that equation of a line? Well, remember, y minus, pick a point, put in your slope, pick another point. I will do y minus 197.6, and to x minus 8, this will be my equation of my line. Guys, we learned a lot of different stuff in this video. You might need to pause it, go back. Please take really good notes on it. Other than that, email me if you have questions, and have a great day.